Okay, so I think we are live. I joined in early just to double check if everything is working. Can you guys hear me and see the slides? Type 1. Okay, cool. Thank you. So maybe we should just wait 2 minutes or so, or 3, just to give people time to join. So for the time being, I'm going to make a coffee. It's quick, I will be back. Turns out the coffee was already made, so. Okay, cool. So thank you so much for being here. Just to double check again, can you see my slide? Cool. Okay, before we start with the actual main session, I will just go through the course stuff. Let me put this thing here. Yeah. So essentially, the course format will be split into things. First of all, this is the foundation module. For those of you who didn't have the chance to attend the course presentation session last month, I will share the YouTube link later. You can check the other 2 advanced modules, but this one is the foundation module. It will run for approximately 12 weeks, 1 lecture per week. So it splits into parts, the lecture part and the course extra part. So the lecture part will have lectures on Fridays, lasting from 45 minutes to 60 minutes per session at 6 p.m. British summer time, followed by live Q&As, 5 to 10 minutes. But I'm also flexible if there is anything more to be said afterwards. And then I will share the self-study materials. These will be like curated self-study materials, like ebooks, free ebooks, for instance, on a particular topic. This is so to help you kind of, so the lectures will be a kind of a guidance really for you, especially for those of you who are new to these things. They will help you kind of, focus on which areas you should be spending more time to prepare for the next lecture. So the lectures are designed to have like these 7 days gap in order to help people observe before the next lecture. So that's the foundation module. I'll go in a bit about what we will cover in the foundation module. In respect to the course extras, we'll have like a fireside chats where we'll invite people from the industry to have like a 1 hour or so Q&As where you can ask them any questions. In fact, one of the things that we're going to try to do is actually to kind of have one of you be like the moderator or to the conductor of the conversation. That way you are actually kind of asking the questions or directing the conversation from your side, not from our side. So I really look forward. I already have like quite a few people ranging from startups to large companies who are willing to come in to do the fireside chat. It will this will be on Tuesdays at 4 p.m. British Summer Time. Next week, I should know more or less about the schedule for the first fireside chat. So there won't be any this coming Tuesday, but hopefully I will update you as soon as possible. And then we'll have group office hours. This will be with me or with my my colleagues, where you can ask anything, whether in respect to the course or career advice or any other stuff that we might be in position to help you with. Let me just check the chat to make sure that everyone is listening. I mean, everyone can hear me. You can still hear me and see the slides, right? Yes, okay, cool, thank you. Okay, so this is what we'll cover in this module. There is a bit of refinement compared to the original idea. The major difference is really that originally we planned to have like a functional analysis in this module, but based on the feedback that we got from you guys, and by the way, thank you for taking the survey, we think it's probably better to push the functional analysis bits of the course to the next module, so we can cover it properly, but also to make this module more or less kind of aligned with standard quantum computing textbooks. So another way to say this is that we're going to focus on finite dimensional Hilbert spaces, really. So the infinite dimensional case will be dealt with in the next module. So today we will just quickly review, and actually that's one of the useful things for the survey, is that a lot of you are coming from university, already have been exposed to mathematics, so no need to go too much into kindergarten stuff in respect to set theory. We'll still have like some basic stuff that we will go through today, but it will be tailored to actually showing you how with some basic concept you can actually recover some powerful stuff. In this case, we're going to use the basic concepts that we will go through in this session to give you a taste of measure theory. And then hopefully you recognize something that we will recover. You will recognize it. So I'll leave that to the lecture bit. You will see what I mean. So the next lecture will be group theory next week. Just the basics that we need in order to for you guys to feel comfortable with the rings and fields. And then after that, we'll move on to complex vector spaces. We'll then move to linear operators in the abstract form, and then the correspondency to the to matrices. We'll then do some matrix analysis, and then we will jump into kind of spending some time with some very interesting groups. The general linear group and the unitary group. These are very important in quantum mechanics, but also in quantum information, in quantum computing. So hopefully you will learn some interesting stuff. And from here, you will already start to see some of the stuff, matrices that you're already kind of dealing with, whether unitary matrices and these things. So another way to see this also is like, this is like a Lie groups 101, really, to prep you, because in the next module, we will cover Lie groups and the algebras. So this is a kind of behind scenes, is just a bit of taste of preparing you for that. And then we'll go through covering the actual Hilbert spaces. Again, we will focus on finite dimensional case. And then we will then focus on the quantum operators. I mean, in the sense of like concrete operators that you normally encounter in textbooks. Hermitian operators and unitary operators and so on. So that's what the refined foundation model looks like at the moment. Obviously, we are very flexible to see how we'll see how it goes, but this is more or less what we think we should cover in the foundation module. Until now, is there any question on this? Yes, the lectures will be available for view later on YouTube, yes. Does anyone have any question about the coverage? Okay, cool. So nobody does have a question. I hope no sound issues from my side. So the approach we will try to make, as already mentioned in the previous presentation is this, more or less this. We start with the abstraction and stay there as long as possible, because this will hopefully help you feel comfortable with the abstraction, because it's in our view that, in my view in particular, that if you are going to create, if you are to have any chances of creating new theories, whether in quantum mechanics or quantum information theory, you need to feel comfortable with the abstraction. So, yeah, we will try to, make it as accessible as possible, but at the same time, kind of help you get kind of comfortable with the abstraction. And then we'll have like concreteness, so abstraction will not be just for the sake of abstraction, it will always be for a purpose of directing you to something that we want you to our goal. And then there's something I call quantum hints. Actually, I convinced myself to change it from quantum contest to quantum hint. Originally, quantum contest, I kind of sense that maybe quantum contest will kind of make it look like we will dive deep into the physics side of things, which is not the case, because this is not a physics course. So if you want to learn physics, it's not here. But hopefully in the future, we might have like an integrated course where we cover the mathematics and physics and possibly the computation side of things. But just to say, but hopefully we'll give you enough hint on how the mathematical objects that you are going to be exposed to are used in both physics and quantum computation. But ultimately, it will be up to you to kind of connect the dots through maybe attending another lecture on quantum mechanics on the physics side, or quantum computation. So this brings me another slide to practical tips. Some of you already seen this because I sent it yesterday. The first thing I want to say is that don't be scared of abstraction, really. And we are aware that through the survey that a lot of you, let us know that you don't feel comfortable with abstraction, but don't be scared. We'll do our best to make the concept as accessible as possible. And sometimes maybe I will, instead of proving things directly or doing, I might go like zigzag just to help you see with the reasoning to drag you along. So in that case, actually, apologies to those who are coming from a mathematical background. If sometimes you think, oh, but you could have done, gone through this or that. But I'm just doing it because there are a lot of significant number of people who said to us that they don't feel comfortable with the abstraction. So we're trying to make kind of as accessible as possible. So another thing I really advise is take a lot of notes, especially notes from yourselves, in the way that you understand the concept that, I will be, my colleague will be conveying to you. It's very important. Another thing is to do online research. If you get stuck, don't feel frustrated if you don't understand something or, these things, sometimes things take time to process. And the good thing is by having this 7 days gap, you will kind of hopefully have the time to process things, but do online research, search for different sources. All this will help you kind of get familiar with the concept that you will be exposed to. Another piece of advice is do a lot of self-study. So the materials we'll share with you, obviously they will contain more than what we cover on the thing. We will just go through summary. As I said in the beginning, these live sessions are more of a kind of helping you, steering you to hopefully to the right direction. So you're not lost with the, kind of on where you should focus or not. So do a lot of self-study and exercise on each particular topics that we cover. So today, for example, we are covering set theory. So, in the next 7 days, go through a lot, as much as you can, through the materials that we'll share with you. And finally, try not multitask. I know it's very hard. A lot of you have your own stuff to do and these things, but multitasking is really, at least I find it very hard kind of focus, because especially in this case, when you miss something, a detail, it's very easy to then you will be lost for the entire lecture, because there's some subtlety in a definition or something that you didn't catch because you were doing something else. So that's definitely something I recommend, to try not multitask while watching the lectures. Or a final thing is to try to attend the live lectures or watch the replay of the previous one before you watch a new lecture, because we'll take this approach of building structure on top of each other. So naturally, if you don't know, say for example, we'll start today with sets, and then next week we'll add a structure on top of a set, which in this case will be group, and then after we'll add rings, and we'll add field. So if you don't know the concept of group, it will be very hard for you to kind of catch up, because of this approach of layered structure that we have decided to take. So yeah. A lot of you have been emailing us about, certification, completion stuff. And it's not easy. We thought a lot about it. How can we kind of issue something to reward you for the efforts that you go through? As it stands, we think the best way for us, for both sides, is probably through a submission of a work. So you learn the mathematical concept or whatever we help you hopefully gain, and then you do something with it. It doesn't have to be, this could be like a theoretical work or a practical work, for example, by that I mean like, contributing to an open source project or creating a new one. It doesn't have to be anything grand. It's just to show us that, you have put the things that you learn into practice. And this is a way of us assessing whether we, this pilot project has had any impact on you. There's no other way for us to judge that. We could give you problem sheets and, you solve, but it doesn't say anything, because, the problem sheet, the problems that you will encounter, these are like problems that anyone else can solve. Well, not anyone else, but you know what I mean. So this is a way of we think is the middle ground for both. And I really encourage group submission, and not least looking at the attendees, your profiles on LinkedIn and other, you have like a very diverse set of attendees. So this will help you with your diversity, maybe to pick up an interesting problem solve. And another reason for doing group submission will be also that maybe some of the mathematical concepts, some of you might find it easier than the other. So by having like a kind of a mixture, you help each other. But you are also welcome to do like individual submission if you like to. So later I will send a Google form where you can decide whether you want individual submission. First of all, you're going to decide whether you want to get a certificate afterwards, after the entire thing. Then afterwards, you decide if you want to do a group or individual submission. For those who decide to do group submission, we'll then we'll create maybe an error table or something, or maybe do some sort of catch up or intro between yourselves. In fact, we're going to create a Slack channel so people can work out who they want to work with. Likewise, if you already have a friend attending the course with you, maybe you can form a group or something. So it's entirely up to you, and we don't cap. There is no cap. Obviously, the larger the group, or probably the harder is judge the input of the individual team members. But yeah, it's entirely up to you. The only condition is that obviously it has to contain some mathematical element. Ideally, things. I'll come back to this again over the next coming days. Another thing before I take questions for this part of the session, and then we'll jump straight to the actual theoretic stuff. The curated materials will be available notice that we have a GitHub repo. This is the repo. You go there and you will see the foundation module, and then inside them you will have lecture 1, lecture 2, and so on. You can also follow us on YouTube, in case sometimes maybe you are not able to attend the live lectures. So it's a way of you kind of be notified whenever we upload a new video. Twitter is also, Slack is coming soon. Over the next coming days, I'm just waiting for confirmation from the company to tell me about the ground rules of Slack, corporate stuff really, but yeah. And then I will send out, it's optional. You don't have to join the Slack group, but yeah, it will also be something we'll announce soon. So this is it. Before I jump to the actual main session, does anyone have a kind of any question? Thank you, Amir and Anne, everyone. Mustafa, will we get certificate of attendance? Let me think about it, really. I think maybe the thing is, how do we kind of know whether people are attending or they just showed up and, you know, that's the thing. So let's say I'm not sure. Can we receive the slides before the start of the next lessons? This is one of the things that we wanted to do, is to send stuff in advance, but then, you know, the idea was that if we send stuff in advance, this will discourage people from attending in the first place. And the other thing is maybe they won't know because the live sessions will have practical advice on, you know, where they should focus on and these things. So yeah, just 1 hour before, yeah, maybe, yeah. Let me think about it and I'll get back to you. Does anyone have another question? Let me stop sharing this and then go to the other slide. Okay. Let's see, where is the share button? I need to find it. Yeah, it's here. Okay. So can everyone see this slide? Type. Yes, okay, cool. Let me maybe maximize it. Yeah, so naive set theory. So we chose a naive set theory as a kind of pedagogical way of teaching, but underpinning that is the Zermelo-Frankel axiomatic system together with something called the axiom of choice. You don't need to know this. I just have to state it because everything in this course, in fact, modern mathematics, at least modern you know, set theoretic mathematics is the standard is really ZFC. You can Google this. There are other people, there are people trying to create foundations of mathematics on things like category and these things, but that's like a fringe stuff. Set theory is the standard, and the ZFC is the standard approach. There are other axiomatic systems, but this is what we will. So the agenda for today is we'll just cover, we'll start first with some frequent mathematical jargons. This is mostly for those who maybe haven't encountered them, because you will encounter these things frequently, not just through our slides, but mostly in the self-study materials also. So it's good if some of you never heard of a jargon, or don't know what it means, to kind of go through some of them. And then we'll go through the basics of set theory, really. It's like a kindergarten stuff, really, since most of you already kind of have like exposure to university level of maths. There is no need for us to go like, we'll just cover the basics, really, And the idea is that as we go along, if we need more set theoretic concept, we can always refresh people on the go. So there's no need to go through too many things. So basics, yeah. And I must tell you the definition of sets is the most uncomfortable parts of this session. Is not easy to define, what a set is, especially using the naive approach. In fact, I remember having a professor of topology many years ago who would skip the first 2 lectures and give it to the assistant because he doesn't want to be the one defining sets and all these things. So he would come in after. So it's not easy to define sets. But hopefully you will agree with the definition that I give. And then we'll have an overview of natural numbers, the integers. This is also for a purpose. We'll kind of have just a quick thing on maps between sets. These are all things that I expect a lot of you already know, so we won't spend really much time about it. Cardinality of sets, we'll define what a finite set is in the mathematical and formal sense, as the same as the infinite sets. And then the notion of countable and uncountable sets. And hopefully, maybe some of you will be shocked with some interesting and nevertheless counterintuitive facts. And then the best part for me is this, what I call measure theory hack. So I wasn't planning to add this because the coverage will just be minimal, but then I thought just to showcase the power of abstraction, this notion that with minimal things you can accomplish a lot. We will do this. You'll have a flavor of a measure theory, and in fact we will recover a notion that hopefully a lot of you will recognize just with some basic stuff that you will go through today. And then after that, I will just do some comments about the material that I will share after the lecture, and then I will open up for session Q&As. On that, I will actually ask, because I know some of you are coming from mathematical background and maybe other backgrounds that are more advanced. If anyone is struggling on the chat, please help them. That way, they don't have to wait for me to go and kind of clarify anything. So it will really be very helpful if you can help each other out on the chat. So that's it really. So let me just, before I go to the first session, let me just check if can you still see me and hear me and see the slides, most importantly. Yes, okay, cool, thank you. Just double checking. Okay, so this is the mathematical jargons, that you will come across, especially this is not for those who are, a lot of you who are like advanced students, you already seen these things, but is there anyone on the audience that hasn't seen something, Is there anything like, what a theorem is? A lot of you, I guess, you've heard of a theorem, Pythagoras theorem, for instance, or for those of you coming from quantum computation, the no cloning theorem, right? So I assume this is not a problem. Yes, so there's no problem with that. What about proposition? Propositions are really like also, let's say, theorems, but they like, mathematicians like to reserve the word theorem for something non-trivial. Well, for something more important, really. So propositions, you will see when you see something like proposition, blah blah blah. In fact, in this session, you will see quite a few of them. It's also a theorem. Lemma, or as I call lemma, or depending on your accent. They are also theorems, but you normally use them for kind of set up the stage to prove something else. Corollary are like the other way around, like consequences. So you prove something, and then as a consequence, you prove something else. I'm being a bit sloppy on on this, but yeah, it's in a nutshell. Conjecture is something that mathematicians think it's true, but there is no kind of proof or disproof of it. In fact, we'll see one example of this in the countable and uncountable thing. Proof, obviously, is proof, though there is I don't want to get into debate about proof. There is a lot of thing even in between mathematicians in the foundation of mathematics. What does a mathematical proof is, you know? In particular, can we trust machines to help us do proof? So I won't go there anyway. So another thing is definitions. You know, you will see this a lot. You know, definition, blah blah blah. You know, definitions are really used to define something that of interest. So I guess that's it really. Does anyone? Yeah. So yeah, I'm glad. Yeah. Well, you will hear a lot of proposition here because in these lectures, a lot of stuff that, you know, I personally don't think it's like deserve to be called theorem. So I'll call them proposition instead. Yes, Anne is saying lemma. Yeah. So, I mean, these are all things that you can Google after to find out these terms. But just to let you know, you will find a lot of these things, you know, in the test books that we share with you and so on. So, I forgot axioms. So axioms are like, if you will, like building blocks. Yeah, thank you, Barry. Thanks. So axioms are really building blocks. You know, they appear not in definitions. So they are the kind of things that you don't need to prove. You know, you kind of, you know, if you give your axioms, people take them for granted. Obviously, there are some ground rules to it. Say, for example, you know, you can't have, say, for example, if you have a group of axioms defining an object, you can't have one axiom saying this and the other one contradicting it. So, you know, that's not the thing. And generally also, okay, I won't say that. I wanted to bring in independence and these things, but yeah, in a nutshell. Okay, so this brings me to the first definition, the hardest, as I said. So, but bear with me. A set is a collection of distinct objects called elements of the set. I told you it's very, very naive. I guess you know you see why the term naive. And I highlighted distinct. Rather than telling you why, some of you might be thinking, you know, why can't I just have collection of things that, you know, why can't we have duplicates and these things, blah, blah, blah. I won't argue with that. I won't say the thing. I want you to conclude, to have the conclusion yourself as we go along making set theoretic constructions. If we didn't have this, how would life be for you in terms of proving some you know, even like elementary stuff? So yeah, I'll leave it to you to convince yourself that you want this. In fact, I would say, say for example, this, you know, if you give a mathematician this, the mathematician will assume you mean this. So, you know, even though here you can look at like, for example, this has like a duplicate twice, a mathematician will work with this instead, and they won't tell you. And if you pressure them, they might come with an argument to say, you know, even though you have given this, what you really mean is this. So don't go there. Another thing is this concept of an element of set X. So mathematicians write this thing here and say, in this case, psi. If psi is an element, first of all, I took the freedom to start using psi. At the moment, psi doesn't mean anything. It's just an element of a set. But deliberately, as we go along and add more structure, say, for example, a vector space structure and then Hilbert space structure, psi will become, you know, what a lot of you already know what psi is. So, yeah. So I added it. I start using it now is just to kind of make people feel, especially those who are not coming from, you know, physics or maths background, to start being familiarized with the psi notation, you know. For the time being, for the next few lectures, until we add the vector space structure, you know, psi is just an element of a set, really. So we write this, if psi is an element of X, and we say psi belongs to X. Otherwise, we write this to indicate psi is not an element, or psi doesn't belong to X. Is an example. Here, X belongs, 6 belongs to X, but 11 doesn't belong to it because there's 11 is not in here. I must also mention the Russell paradox, which kind of, especially with the kind of a naive set theory, it's really a trap. So first of all, looking at this, so let S be the set of all sets which are not elements of themselves. In other words, let S be A such that A doesn't belong to itself. Let me just ask, especially not to the advanced students, to attendees, sorry, to the others, can you see what's the problem with this? Can you see a contradiction there? When you ask a question, if S belongs to itself, can everyone see? Is there anyone who doesn't see a contradiction? Okay, so I assume everyone sees it. That's great. So, in fact, I'll just double check. Can everyone still hear me? Yeah, okay, cool. So yeah, so you probably kind of, yeah, okay, cool. So you probably already came across the Russell paradox before, so it's not a surprise to you. Here's a popular version of it, which is, consider a barber who shaves all people who don't shave themselves. So if you ask the barber if he shaves himself, if he says yes, then it's no, because he only shaves people who don't shave themselves. If he says no, then it's yes. So yeah, so the point to make here is in naive set theory, especially when you use what we call like set builders, it's very easy to build sets, to build something that looks like a set, and then that leads you to contradiction. So in the axiomatic, like the Zermelo-Frankel axiomatic system, this is not a set. It might look like a set, but it is not. So that's the point really I wanted to about defining. I see. Okay, sound is cutting out. What about now? Okay, cool. Oh, I apologize for that. Maybe my networking. Yeah. Okay. Another important thing. First of all, just to confirm, can you see the next slide? Yeah. Okay, cool. So another very important notion in set theory is the empty set. And normally people who are not coming from a mathematical background tend to overlook it, but it's very important construct in at least set theoretic mathematics. In fact, I claim that without the empty set, modern mathematics, at least set theoretic mathematics would not, or anything built on set theory will not work without function properly without the empty set. I put these examples. For example, to define the notion of topology, you need the empty set. So without the empty set, you will have a trouble defining the notion of topology. Without topology on a set, you cannot, of course, talk about topological spaces. Without topological spaces, you cannot talk about topological manifolds. And without topological manifolds, you cannot talk about differentiable manifolds and so on. It's the same in say measure theory, for instance. So it's really a very important construct that normally is overlooked. But mathematics without the empty set, at least set theoretic matter, would be like being in a cruise ship in a very rough waters with no stabilizers. Everything will be like maybe capsized. So yeah. If somebody disagrees, I'll pull you at the end of the thing to tell me that to make your point why you think the empty set is not important. Okay. Just double checking again. You can hear me. Nothing is cutting, right? Okay, good. Okay, so that's the empty set. So the empty set is your best friend. And then another definition I'm going to go is a subset. So if A, we say A is a subset of X, and we write this. If when psi belongs to A, it also means psi belongs to X. So psi belongs to A implies, so this arrow here means imply psi belongs to X too. And we write this otherwise. And one of the obvious consequences is that, obviously, any set is a subset of itself. Now, this question, mostly not for the people coming from mathematics or other more advanced attendees, the other ones, is the empty set a subset of X? Who thinks it's not? Okay, I will let you. What I will do is, think it through first. I claim maybe you are answering it not using your human intuition, not the mathematical intuition. So take it through, maybe a few days. Go back again and these things, and then at the start of the next session next week, we can come back to see if you agree. But yes, the empty set is, in fact, the empty set is a subset of any set. Okay, so then obvious consequences, obviously this, I won't even spend time on this. Obviously, if you have three sets and X is a subset of Y and Y is a subset of Z, then obviously X is a subset of Z. You will have this slide anyway, so I won't, this is like kindergarten stuff. Another definition then is the definition of equality. So we say two sets are equal if they are contained in each other. So for example, this is again another trick. So let's X be psi 1, psi 2, psi 3, psi 4, psi 5, blah, 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 and then let's Y be this. Does anyone think these two sets are different? Okay, good. So yeah, indeed they are the same. I haven't made any assumptions whatsoever about the ordering and all this. So for those not for the advanced, this is more for the advice of those who are the newbie, not coming from a mathematical background. It's generally when you are given something, don't assume anything extra that you're not given. In here, I'm saying that assuming only the definitions that we have gone through so far. So assuming those, then we can obviously see there's nothing, because any element of X is also an element. You can find them, even though the ordering, I shuffled the ordering, it doesn't matter. I made no claims about order. So it's true. Another definition is that of a proper subset. So we say A is a proper subset of X if A is different than X. In other words, if not all elements of X are in A. So for example, using the example of X equals this, obviously this is a proper subset of X because there are some elements missing. So I assume this is also, piece in the cake. Yeah. So the next is natural numbers and integers. This is something that we learn. Is like, some of you might be thinking why we even have to come through this, but it's very important. So the set of natural numbers is often in the textbooks defined like this. So just in case in the future or whatever you come across, it's generally not. It's generally optional to It's still a debate whether 0 should be classed as a natural number or not. However, it's a very useful construct. So to use it, what mathematicians tend to do is to add another set called n0 and then add it there. Of course, then we have like an extra element. N is, of course, then a proper subset of n0, right? So, and the same here, the set of integers which contains the natural numbers and 0. So n0 is, of course, a proper subset of z. Just out of curiosity, you won't see this until we go. This is with one of the surprises I was saying. Is there anyone who thinks that z has more elements than n, for instance? Okay. 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 What about, so is there anyone who okay. Okay, I have in the next the time when we reach to the concept of countability and these things, you will have a surprise actually on this. So let me proceed. Again, this is like a normal definition that most of you have heard of. So bear with me. I only have a few slides to go before we go to the main thing that I wanted, the measures part. But intersection is defined like this. So intersection of x and y is a set containing all the elements psi such that, so this vertical line here, this means it's abbreviation for such that. Often in notation, you also use a colon, but I prefer using this whenever I'm using set builders instead of a colon. So a nice way of visualizing intersection is this. So you have an intersection. The intersection is this, where the two sets meet. So this is also kindergarten stuff. It's clear, I guess. The union, on the other hand, is defined like this. All the elements psi such that psi belongs to x or psi belongs to y. But bear in mind that the union can also have elements that are in both sets. So that's something you need to bear in mind. And then we have this that all of you can prove. You have the commutativity, these terms that I suggest in your self-study, you kind of get familiarized with this and try to solve this. This is like kindergarten stuff. I'm pretty sure you will be able to prove this. Another important notion that you should know is the, first of all, two sets are disjoint if their intersection is empty. So you see, another reason why the empty set is very important. Without the empty set, then the intersection between sets will not be defined for every set. It would only be defined for those sets that have something in common. So yeah, this is a typical. This is another thing that reinforces why the empty set is important. So two sets, we say they are disjoint if their intersection is the empty set. And then you have another definition, which is the complement. The complement of A in X, defined like this. Some people use a bar, but I like to use C. So it's defined as psi in X such that psi doesn't belong to A. So in other words, the set of all elements of X that are not in A. So essentially this shaded area here. Let me double check again. Okay, cool. So I assume everyone is hearing properly. So I will go. Again, this is like another simple thing that you can prove later. It's really very simple. Important thing is obviously the relationship between sets. So this is again a kindergarten stuff, but I want to just comment on a few things that later on will be very important. So a map is really, or a function, I like using the term map, but in some books like the one that we will share today, the author uses the word function. So he's not using the term map. So it means the same thing. So it's I like to call it a prescription, that associates an element of X with an element of Y, and not necessarily all the elements of X, because it depends on your prescription, and that actually has a special name. The set of all covered elements of X under the map F is called the domain of F, and in here today, for example, we'll call it the DF. So the set of all elements where F is defined, So a map doesn't have to be defined on the entire set, In fact, this is one of the quantum hints. When you deal with the infinite dimensional Hilbert spaces, especially with the so-called unbounded operators, this will become very important to know, what domain you are working on. So the concept, that's one of the reasons that I'm highlighting this. So for each psi belongs to df, we write f of psi to denote the corresponding element in Y. This is, again, for most of you, this will be kindergarten stuff. And then the set of all f of psi's, so the set of all elements of Y that are mapped from elements of X is called the image of F. So im of F is defined as f of psi such that psi belong to the domain of F. So it's just another kindergarten example. So you have the domain here. So you have the set X, you have the domain, and the domain, you can see there are some elements here that are left out. So F doesn't cover these elements, but it covers this. And you can also see that, we have two elements corresponding to the same elements in Y. This can happen. So this motivates to go to the next definition, which is this one. It says when you have a map from X to Y, it is called surjective if the image of F equals Y. In other words, for all, this inverted A means for all. So for those of you who are new to this, take a note. You will see this a lot. Not necessarily in this lecture, but whenever you see this, it means for all. So this means for all phi in Y, there exists at least a phi. There exists a phi such that phi equals f of psi. It is injective if you have equality in the image only if the psi's are equal. And then we say it's bijective if it's both surjective and injective. This means that it's one-to-one, essentially. So for each element in X, you send one element into Y. In other words, this means the domain of F is the entire set X, and the image of the map F is the entire target Y. Let's see. Yes. Thank you, Ryan. Different terms you will see. In fact, in linear algebra, we'll use the term range because the standard textbooks use the word range, and but it's good. There are different terminology. It's actually, this is very interesting because one of the things that you need to learn, especially when you're studying mathematics, a lot of stuff are like depending on the author. A lot of the terms, sometimes you might like kind of some terms, are used in like particular type of demographics in mathematics, So one thing I noticed, Americans use a lot the term range. This is one of the things I noticed as opposed to Europeans. This is just my observation. It might not be like the thing. So, maybe you can test this, check a lot of books written by Americans and Europeans, you'll see. Anyway, another important definition is this concept of isomorphism. In this case, we haven't added any structure yet. It's a little bit rather boring concept of isomorphism, but we say X is isomorphic to Y and write this thing if there is a bijection between the two sets. So there's one-to-one the thing. And then we write this thing. You will see this a lot. So in the textbooks, if you see this, it means that these two sets are, are isomorphic. You can kind of do one-to-one correspondence with them. Once you start adding more structure to the sets, this is where things become more interesting. For example, when you add a linear structure, like a vector space structure, all it means like the two vector spaces are essentially the same thing. It's just, it's probably, let me be like, an analogy would be like ice and water, is just, they look different, but it's the same. You can, from one, you can have the other one. Yeah, maybe it's not the cleanest analogy, but yeah. This is in algebra. In topology, you have the concept of homeomorphism and so on. But don't worry with that. We will get there as we go along. For now, this is just set theoretic isomorphism. And obviously, if X is isomorphic to Y and Y is isomorphic to Z, it follows that X is also isomorphic to Z. So let's see. Okay, so I assume there is no cut. Everyone can hear me properly. And I hope you are not sleeping, because this is all like boring stuff that probably a lot of you have come across. Here's this interesting stuff start coming. The cardinality of sets. So let's look at the definition. The first one. A non-empty set is finite if there exists a natural number greater or equals to 1 such that X is isomorphic to nk, which is defined as from 1 to k. So now you see why we needed the notion of isomorphism. So whenever there is such a k, we say X is finite. We call the k the cardinality of X. I could have also said X is infinite if there isn't such a k. But I rather prefer this one here. Maybe some of you might not think, but yeah. Obviously, this is something you can prove, that if you have K1, K2, these two are isomorphic if and only if K1 equals to K2. And then this is the thing. I've chosen this definition. X is infinite if it contains a proper subset. You remember what a proper subset is? Such that lambda is isomorphic to X. So that means X is infinite if it can be put in one-to-one correspondence with its proper subset. Isn't this shocking? Is there anyone not shocked yet? Or maybe... Okay, good. Yeah. So this is pretty much kind of counterintuitive to our human intuition, right? This is where we're saying, in mathematics, human intuition is very dangerous, So, this is non-intuitive at all. So in this case, here are examples. Let's look at N0. We know that N0 has the 0, whereas N doesn't have the 0. Looking at this, you ask a human, maybe a child that doesn't know about, what isomorphism, they will say, no, they will probably say these sets are not the thing, but it's true that these two sets are isomorphic, and even more shocking, even though set Z has the negative number and has the N itself, they are isomorphic. Yeah, it's very counterintuitive. Yeah, so let's see how we can show this. So here's the thing. So imagine this. Apologies for this. I had to do this with PowerPoint and get my LaTeX thing, and so it's not a good quality image. But here's F. And here's N on the top. So, for 0, you associate 1. For 1, you associate 2, blah, blah, blah. So for N, arbitrary N, you associate N plus 1. So this is the so-called successor map. You can easily show that this is a bijection. So therefore, N0 is isomorphic to N. So this means, we will see, this means the same, they have the same size. So the same number of elements, even though, this one, in the human intuition might look like this one has more elements because it has a 0, the other one doesn't. So, yeah. Is it understood? Okay, cool. Thank you, Ryan. With Z, we can do similar thing, but I'll leave this to homework for you. So you have, let's say, N0. Let's do the other way around. So you have 0, you're supposed to be 0, minus 1, you're supposed to be with 1, with the 1, you're supposed to do blah, blah, blah. You know, it's also possible, you know. So as a homework, I want you to find what corresponding function that could do this. Or even better, you can find another bijection between N and Z. So let me go back to the section. Okay. So this comes into the concept of countably infinite and uncountable. So countable sets and uncountable sets. So we say a set is countably infinite if it is isomorphic to N. Else, we say, if it's not isomorphic to N, we say it's uncountably infinite or just uncountable. So this means we need to be careful. There are two types of infinites here. They are named below, but yeah. So this is very counterintuitive, I assume, for, you know, not like the ones who, some of you are not coming from a maths or perhaps physics background who haven't seen this before, but, you know, so we need to be careful when we talk about, you know, infinite sets, you know, what we mean. This is very important. The reason why we are touching it, because again, let me give the quantum hint. In the infinite dimensional Hilbert spaces, you want Hilbert spaces with countable bases. So therefore, you know, to save us having to define the concept of countability in the future lectures, this is why we are defining it. So you want Hilbert spaces with countable bases. So bases that you can put into one-to-one with a subset of N. So by definition, N and Z are countably infinite because obviously Z is, first of all, N is isomorphic to itself and it's isomorphic to Z. So now, this question will not be for those who are mathematicians or the 10 who knows. What about the set of rational numbers? Who thinks the set of rational numbers is countable? Okay, so does that mean? Yes, it is countable indeed. What about the set of real numbers? Yes, okay, good. Thank you, Nicholas. We won't show the proof of this, but I'll share some materials after. You can see there's a beautiful theorem called the Cantor's diagonal theorem that shows this. So this is actually ironically this fits in our intuition, because if you look at it, you know, R is larger than Q. You know, I mean, R is Q is contained in R. So this, ironically, you could, yeah, it holds that R is bigger than Q. Now, the cardinality of countably infinite sets is called this thing here. I don't even know how to retain. You can just read it Aleph null or Aleph 0, whatever. And for the case of real numbers, the cardinality of R is called C. It's called continuum. And it's an open problem to say if there is a set S, if one can construct a set X whose cardinality is between N and this. This is called the continuum hypothesis. So it's an open problem. So if one day you wake up and well, first of all, a lot of great mathematicians try to solve this problem. So if one day you wake up and think you have a solution, you probably haven't. No, I'm joking. And if you were drinking the night before, you definitely didn't. No, I'm joking. It's a very interesting problem. I won't even touch the thing to do with the yeah, I won't touch that. There's no need. Just make things a little bit more. Okay, so so far, are we clear here about the notion of countable sets and uncountable? Is there anyone who have any doubts about, what does it mean when we say, so in the future lectures, when we say, here's an Hilbert space, here's a basis, is this basis countable? You know what to do. All you have to do is to check whether you can, do a bijection with, between that basis with a subset of n. So that's what we mean with the countable. So we are not interested in spaces with uncountable bases. There are, so. Which is why, actually, this is again another quantum hint. I know we are not there yet. Why you want to deal with the so-called separable Hilbert spaces. They are the ones who have this property that we want, having like countable bases. Okay. Power sets. This is another very important definition. So if we have X, a non-empty set, the power set of X is defined as a set of all subsets of X. So more formally, the elements of the power set are A such that A is contained in X. So obviously, as we already seen, X is obviously, and because the empty set is also a subset of X, so they are both in the power set. I assume there's no one who disagree, right? So, so for example, look at this. Hopefully I've done the pair. If somebody sees any missing, please let me know. I've been rushing this morning, lastminute.com, to put the slides together. But yeah, so if you have X, hopefully this is the power set of X. These are all the possible subsets of X. Here's another interesting example. The power set of this, you have this. In general, if you can prove that if X is finite, with k elements, then the power set has 2 to the k elements. And it's also interesting that the power set of this is the same as R. Now, actually, I'm going to revert back before we go to the main part of this thing. I'll just ask you, those of you who will see immediate, so we'll go to the measure theoretic part of things, the hack that I mentioned in the early presentation. For those of you who recognize what this map is, do not say anything yet. Let's just see if more people will recognize what we are trying to construct, just based on the few concepts that we went through. So let's see. So let's omega be a non-empty set, and let's define a. Oh, sorry. I spoiled it. Apologies. Okay, that's it. It's spoiled. You already know what mu is. So yeah, but nevertheless, I'll go through it. This is what happens with the slides and these things. So let's define mu as a map from the power set to R. So mu maps subsets of omega to R, and it satisfies the following axioms. The first axiom is that mu of E is greater or equals to 0 for all E in the domain of mu. Apologies. Okay, so that means mu is let's say it's positive. It cannot take negative values. Okay, so it's either 0 or negative. Sorry, positive. And then the second axiom says for every E in the domain of mu, it is also that the complement of E is also in the domain. Okay, so that's the second axiom. The third axiom says that for all E1, E2 in the domain of mu, such that their intersection is empty, so they are disjoint, mu of E union with the, mu of E1 union with the E2 equals the mu of the sum of the two parts. So mu of E1 plus mu of E2. We can also generalize. This is also the thing. I did it this way to not make it too abstract. It is possible that you can for countably many E's that are disjoint, you also have this. This is also satisfied. Mu of E1 union with E2, blah blah blah, is equals to the sum of the individual mu's. So I already spoiled this. I don't even want to ask. Nevertheless, I will ask. You already know what mu is or where I'm trying to head. Can someone see what mu is? Can you confirm all? You already seen the other slides when I went through what I wanted to. First of all, can you type yes if you can hear me and see the slide, just to make sure I'm not disconnected? Okay, yeah. Okay, thank you so much. So I'm asking if you already seen. Is it of you already seen the other slide? So you probably have a hint of what mu might be. I'm just asking. Okay, good. Okay, anyone else who cannot see? Ah, okay, good. Okay. So is there anyone who can see what mu might be? Okay, so let me help you by going to another slide that hopefully, okay, so based on these axioms, first of all, we can prove this, that the empty set is also in the domain of mu, and that the mu of the empty set equals 0. Another thing we can prove is that mu of E is less or equals to 1 for all E in DU. Let me ask again. Can you see what this might be? Yes, it is. This is the abstract thing. This is probability. So this is called probability measure. So, you can see, I don't even, because you already figured it out, you can read this after to see the proof. This is exactly the thing. You can see how with the measure theory, with just, some basic concept, you can, recover something so fundamental, so important. Yeah. So this is, from a mathematician's point of view, this is what probability is. It's just a measure from the power set. So omega would be the sample space. It doesn't matter whether it's continuous or discrete. And in fact, this is what Andrei Kolmogorov figured out when he used the language of measure theory to give a precise mathematical foundation to probability theory, which before that, it wasn't really. It was all like, case by case, when you're doing like building a probabilistic model, you have to go through all these, it was a mess. But through his work, using the language of measure theory, you have like this unified framework for building probabilistic models. So it's really powerful. And you can see from like, just some basic examples, some basic concepts that we cover, like that might look like kindergarten stuff. You can recover this. I actually have this copy of this. I will also attach it to the thing, so you can read his original work. The foundation, his work. I have I think a scanned version of it. I will upload this also to the lecture slides. Yeah. So yeah. So this is it really. So congratulations, you now know what probability is. All is it's a measure, is a measure from the power set or parts of the power set. In fact, this DU, this is what we call sigma algebra. This has that's therefore the title, without mentioning sigma algebra. So under the cover, this is DU. The domain is actually a sigma algebra. We won't go through it because this is not a lecture on measure theory, but later towards the end, in the next module, we will cover measure theory in a much more precise manner. So yeah, and as a homework, this is a challenge. This is nothing. It's if you want, you can do it, but I guess it will kind of be very helpful to you to try to build a measure map, assuming that omega is a discrete set. For example, this could be like imagine a scenario of a rolling die, for instance. So so the challenge for you is for you to build a mu. Just remember, all you have to do is come up with the mu that satisfy this. So whatever way you decide to build mu, just go and tick the boxes. If mu satisfies this, first you consider what could the domain be. I guess in this case, you will want to first get the power set of this, and then see which part of the power set, based on your on how you build this discrete sample space, you want to build the mu for. So this is a challenge for you. So this is it really for, as you can see, this was like a very simple, kindergarten stuff really, but hopefully the last part, this is the part that I was more excited about, to kind of show that with simple stuff, you can accomplish a lot thanks to the power of abstraction, So in terms of set theory, there are a lot of things that we didn't cover in the thing, like Cartesian product, composition of maps, equivalence relations and equivalence classes, index and cell, blah, blah, blah. But the material that I will share with you will have all these things. If you have time, you can get into these things. But if you don't have, don't worry. These are things that we will come to it as we need them in the future lectures. But it will be good if you have time and you get your head wrapped into these things. That brings me to the material that I will share with you. So we try to kind of get like a free resources for you. It's also helpful to us because it means we don't have time to actually produce our own. So we, apart from our slides, so if there are anything open, interesting stuff that's free out there available, we will get it for you. And this one, this free book. By the way, you can visit the Open Sony website. They have a lot of other books in other topics, very interesting. So in this book, these are the sections that I think you should focus. First of all is the section 4 about sets. You will have like exercises, challenges, you name it, all will be here. And then section 6 about maps or functions, you will. And then if for some of you, especially the ones that are not coming from mathematics or possibly computer science and these things, if you can review this will also be nice for you in going forward to see how things are interrelated. But these two things are the most important for you leading up to our next session on the basics of group theory. With that, actually this author, I was just scanning this quickly when my colleague shared this resource with me. One of his quotes, I found it very interesting. It says, all mathematics courses are difficult, and it's true. And you will find this as we go along. It takes hard work and patience, it's true. And most importantly, memorization does not work. So you have to understand stuff, And yeah, it's really kind of very important for you to put on the effort to kind of if you want to really get most out of this, the self-study will be very important for you, and it's very important for you to kind of take as much as time to get these concepts familiarized with you. And I hope this guidance in where you should focus is helpful. With that, I'll stop sharing. And I'll see if well, thank you, Amir. Yeah, I wasn't saying it's like kindergarten stuff, but yeah, it's like just it's not that advanced. You will come to things that are more advanced, but because we are taking this layered approach, hopefully, you will have for each lecture before the next one, you will have enough tool to kind of be able to follow the next one and and the next one and so on. Yeah. So with that, those who have questions or those who don't have and want to leave, please feel free. Let me activate the Q&A if anyone has a question, so everyone else can see it later. Does anyone have any question? Oh, thank you. Thank you, everyone. It's really a pleasure. This was really interesting. I hope, even though it was a very basic thing, hopefully we have enough to build, and you also have a sense of the style that I will be kind of pursuing going forward. Okay, so I have a question. You use the term covered. Let's see. Let me share again to see which section was this one. Was this when I was talking about? Let me click first. Start answering. Was this when I was talking about the maps, Amir? Okay. Let me go back to the domain thing. Yeah. So. And let me share the screen first, so everyone can see. Yeah, so Barry, the question is on the ask question on the thing. You should see at the bottom. Yeah, let me share, if I can find the share button. Chrome tab. Is it this one? I hope. Yeah. So Amir is asking the set of all covered. Yeah. So what I mean is a map. So a map is going from X to Y. It doesn't have to cover all the elements of X. That's what I mean. The covered elements, the elements for which the map is defined. So in this case, for example, here, the covered elements are these, whereas these ones are not covered. That's what I meant, if that makes sense. Does that answer to your question, Amir? So what I mean with the covered the thing is just normally in the intro test to set theory maps and these things, they assume the entire domain is X to make it easy for the thing. But because we are dealing with just to prepare you for Hilbert spaces where domains, your domain is very important. I'm already starting to kind of hit you with this to know that you need not. The domain doesn't have to be the entire set. So the covered elements, what I mean is this, like the elements on the origin, on the source set, doesn't have to be the entire thing. So I hope that answers. Oh, I have another question. So Amir, I assume this is answers your question. Is that correct? Before I move to the next one. Okay, thank you. Okay, so where is this? So the next one, what is Aleph? It was okay. So this is okay. So let me start answering first. Let me go back to this slide. So Nicholas is asking, where is this? It's here. Yeah. So this is just a name. You know, the name of the cardinality. You know. So if it's countably infinite, it means that its cardinal it has the cardinality of n. So we say it has Aleph null. That's what I mean. If that answers your question, it's just a labeling. It's just a name, a term. It's just a term to say like you know, X is countable. You know, in other words, is isomorphic to n. Okay. Okay. So this is done. Are there sets called? So the question is, are there sets uncountable? No. Well, if countable finite, when you say already countable, it means you can count with a subset, because a finite set is a subset of n. So countable is already so a finite set is already countable because it's, you know, you can put it into you know. Let me go back again. So any finite subset is any finite set is countable. So you just say countable. Yes. Okay. So any other question? I mean, for the countability of stuff is like, yeah, actually, it's very interesting. You can look at, there might be some videos that you can watch about Hilbert's infinite hotel. You know, I've seen one that's very funny, actually, well explained. It shows this concept very nicely. So if you search Hilbert infinite hotel, you will see where you have like a hotel with infinite rooms, and then, you know, you bring in infinite number of guests. You know, can you accommodate them? Yes, you can. You can just you know, move guest number or whatever to the next. It's very interesting. Yeah. So this actually the whole thing of this was all like a massive shock to mathematicians. If you are shocked, the thing, you are not. Mathematicians were also very shocked in the 20th century. So, you know, so yeah, I think so. Aditya, thank you so. Yeah, I think so. From the TED, I think it's very funny. So Andy is saying your answer to Nicholas was Aleph is just, but I thought Nicholas was asking, hey, not quite. And is that the case, Nicholas? Just curious if there is a term called Aleph 1. Ah, yeah, there are different Alephs. Yeah, there are actually. I didn't mention that, but that's not something that I want to go to here. There are different. Actually, there are the cardinalities that we have. There are. Yeah. Sorry for that. Yes, there are different. You know. But for most, this is the thing. Also, for most practical stuff that, you know, for us, certainly for this thing, you don't need to think about the other stuff. In fact, I advise you to not think about the other aleph, because you're going to confuse yourself. You'll probably want to go and become someone working on the foundations of mathematics, and logics and these things. And actually, on that, I would say if the slides, can you still see the slides? I wanted to say, the power set for our purposes, you don't have to go like. It's feasible. It's very tempting to go like the power set of the power set, or even the power set of the power set of the power set of the power set, and so on. Do not do that. Don't do that. You will. So, yeah, exactly. I mean, you will go insane, But nevertheless, very interesting. But for our purposes, in fact, for most mathematicians, for most purposes, whether you work with topology, or measure theory or anything, the power set at this level, the power set of X is sufficient for you. You don't have to go the power set of the power set or the power set of the power set and these things. So, in fact, I kind of it's interesting to think about it, but I would definitely not think about it. I haven't been thinking about it myself. So, yeah. Yes, Cantor actually had, yeah, exactly. So, yeah. So, I'll just stop sharing the screen. Does anyone have any other question? If not, we can close it here. I'll send more info about, the group work submission stuff for those who want to be, want to submit things at the end of the course or something. So you can start kind of connecting with each other. Also about Slack. Once the Slack channel is active, I will send out kind of I'll let you know. So those who want to join Slack can opt in, So yeah. So that's it for now. And yeah, I hope, even though it was a very basic session, hopefully the last part of it, when you can see like with the little you can do so much, thanks to abstraction, it was worthwhile. So yeah. So thank you so much. And yeah, I will be uploading. Don't forget to check the GitHub repo and yeah, and get the lecture materials. And I'll see you next week when we go over group theory. So okay, so thank you again. And yeah, don't forget the YouTube video should be live in a few hours time also. So yeah, so have a very good weekend. Thank you for tuning in, and I look forward to seeing you. Okay, thank you.